What if quantum entanglement reveals that reality is more connected than it looks? Two particles meet. They interact for a moment, then they separate. One goes one way, the other goes another way. They can end up far apart, very far apart. And yet, when scientists measure one of them, the result is linked to the other in a way that seems impossible at first. That strange connection is called quantum entanglement. It is one of the most famous ideas in modern physics. It is also one of the most misunderstood, because when people first hear about entanglement, it sounds like science fiction. It sounds mystical. It sounds like particles are secretly talking to each other across space. But that is not really what physicists mean. And the truth is even stranger than that. Quantum entanglement comes from quantum mechanics, the branch of physics that describes nature at the smallest scales. It deals with things like electrons, photons, atoms, and other tiny parts of reality. At our everyday scale, the world feels simple. A ball is here or there, a light is on or off, a coin is heads or tails. We assume things already have their properties, even before we look. That way of thinking works very well in ordinary life. It also works in a lot of classical physics. But the quantum world does not behave like ordinary life, and entanglement is one of the clearest examples of that. To understand why, imagine something simple. Picture two boxes. Inside the boxes are two gloves, one left glove and one right glove. You send one box to one city and the other box to another city. When someone opens the first box and finds the left glove, they instantly know the other box contains the right glove. That is not mysterious. Nothing magical happened. The gloves were already what they were from the start. That is how common sense tries to understand entanglement. Maybe people think the particles were like those gloves. Maybe each one already had hidden instructions built in. Maybe the weirdness is only because we did not know the answer yet. That sounds reasonable. In fact, Einstein was deeply uncomfortable with quantum mechanics for exactly that reason. He believed the theory might be incomplete. He suspected that hidden information might exist underneath the strange behavior. He even used a famous phrase for the idea that bothered him. He called it spooky action at a distance. Einstein did not like the possibility that nature could be that weird. And honestly, most people still feel the same way. But then physics went further. A physicist named John Bell showed that if particles were only carrying hidden local instructions, then there should be a limit to how strong their correlations could be. That limit became part of what are called Bell inequalities. And when scientists tested those ideas in real experiments, the results were shocking. Nature violated those limits. Again and again, the experiments matched quantum mechanics better than the old common sense picture. That does not mean one particle sends a usable message to the other faster than light. That part matters a lot. Entanglement cannot be used like instant texting across the universe. You cannot force one particle to send a custom message to the other. So this is not faster than light communication in the normal sense. What it means is more subtle. It means the connection between the particles is deeper than the idea of two separate objects carrying separate private instructions. And that is the real key to understanding entanglement. The best beginner-friendly way to think about it is this. Sometimes two particles are not best described as two separate things. Sometimes they are best described as one shared system. That is the shift, not two little objects with secret labels. One combined quantum state. That may sound abstract, but it changes everything. Because in normal thinking, we imagine reality as a collection of separate pieces. This object has its own properties. That object has its own properties. Each thing is fully itself. Entanglement says that picture is not always deep enough. Sometimes the most accurate description is not about each particle alone. Sometimes the real description only exists at the level of the pair. In other words, the relationship is fundamental. That is why entanglement feels so hard to grasp. We are trying to understand it with a brain trained by everyday survival. Our intuition was built for stones, trees, distance, bodies, movement, and simple cause and effect. It was not built for quantum reality. A useful metaphor is music. Imagine two notes played separately. Each note has its own identity. Now imagine a chord. A chord is not just one note plus another note in isolation. Its meaning comes from the combination. The pattern matters. The relationship matters. Entangled particles are a little like that. Not identical to that, of course, but close enough to help. Another way to picture it is like a dance. Two dancers perform a routine so tightly linked that you cannot fully describe one dancer's role without the other. The whole choreography matters more than either person alone. When one part is revealed, the structure of the whole becomes clearer. That does not mean one dancer secretly shouted instructions across the room at the last second. It means the deeper truth was in the shared pattern all along. That is much closer to what entanglement is pointing toward. This is where many beginners get confused. They hear that measuring one particle affects what we can say about the other. Then they imagine a signal flying through space. But quantum mechanics does not require a little beam of information rushing from one particle to the other when you measure it. The weirdness is not ordinary communication. The weirdness is that the universe allows correlations that seem to come from a shared underlying state rather than from separate local properties. That is a very different idea. And it is one reason quantum theory feels less like a machine made of tiny marbles and more like a system built from probabilities, patterns, and linked possibilities. This also connects to another famous quantum idea: superposition. Before measurement, a quantum system is not always sitting there with one simple definite value in the way classical intuition expects. It is described by a range of possibilities, and when particles interact, those possibilities can become entangled, so their possible outcomes are no longer independent. That is what makes the results so strange. The future of one is mathematically tied to the future of the other. Again, not because they are sending secret messages in the ordinary sense, but because they are part of one quantum description. And the deeper you sit with that idea, the more radical it becomes, because it challenges one of the most basic assumptions of common sense, that distance automatically means independence. In daily life, distance usually means separation. If two things are far apart, we assume they are fully independent unless something physically travels between them. Entanglement tells us that at the quantum level, this picture is incomplete. Space still matters, distance still matters, relativity still matters, but separation is not as absolute as it first appears. And this is not just philosophy. Entanglement is not some poetic idea floating around in science documentaries. It is a real feature of quantum theory that has been tested experimentally and is now part of serious technology research. It plays a role in quantum cryptography, where the laws of physics can help reveal whether information has been intercepted. It also matters in quantum computing because entangled states allow information to be processed in ways that classical systems cannot easily imitate. So this is not just weird for the sake of being weird. It is weird in a way that appears to be built into reality. And that has consequences beyond physics, because entanglement changes how we think about knowledge itself. In the classical picture, measurement feels simple. Reality already has the answer. You just go look at it. In quantum physics, measurement is more subtle than that. It is not always just revealing a pre-written property in the old-fashioned sense. That does not mean human consciousness magically creates the universe. A detector can count as a measurement. An interaction with the environment can matter. You do not need a mystical human mind floating above the experiment. But it does mean that the line between what is possible and what becomes definite is more complicated than most people imagine. And that is where entanglement becomes deeply interesting even for non-physicists. Because once you understand it, even in a basic way, you start to see that reality may not be built from isolated things first. Maybe, at the deepest level, relations matter as much as objects. Maybe the universe is not only made of pieces. Maybe it is also made of connections. If that is true, then entanglement is not just a technical result in physics. It is a clue about the structure of the world. A clue that our normal mental model is useful, but incomplete. A clue that common sense works at human scale, while deeper reality may follow stranger rules. And there is also a practical lesson hidden inside this. Human beings often try to understand everything by breaking it into parts. That method is powerful. Science depends on it. But entanglement reminds us that sometimes the truth is not fully inside the pieces. Sometimes the truth is in the relation between them. That idea shows up everywhere. In biology, context matters. In systems, networks matter. In human life, meaning often depends on relationships, not isolated units. Of course, we should be careful. Quantum entanglement does not prove every mystical claim people make online. It does not automatically explain consciousness, destiny, telepathy, or spirituality. A lot of people borrow the language of quantum physics just because it sounds profound. But real science is more disciplined than that. The honest lesson is not that everything mystical has been confirmed. The honest lesson is that reality is stranger than old intuition expected, and science discovered that strangeness through rigor, not vagueness. So if you want the simplest explanation possible, here it is. Quantum entanglement happens when two particles become part of one shared quantum state, so that when one is measured, the result is correlated with the other in a way that cannot be explained by ordinary local hidden instructions. That is why physicists care, and that is why regular people should care too, because entanglement is not just a bizarre detail from the microscopic world. It is a warning that reality does not have to match intuition, a warning that distance does not always mean full independence, a warning that what looks separate on the surface may belong to something deeper underneath. Quantum entanglement does not tell us that the universe is magical. It tells us something more serious, that the universe is real enough to resist our assumptions, and strange enough to force us to think again. Lucid order. Question everything.